Imagine a standard sewing needle hurtling through the silent void of space directly toward our planet at the speed of light. At first glance, a tiny sliver of metal seems harmless against the vastness of the Earth. However, when an object moves at light speed, the rules of physics change everything into a nightmare of destruction. To understand the scale, let's define exactly what the speed of light entails in empty space. Light travels so fast that it could circle our entire planet 7.5 times in a single second. Consider a trip to the moon, which sits over 386,000 kilometers away from us. A standard modern spacecraft takes about 3 days to complete that long journey through the dark. Traveling at light speed, that same 3-day trip would take you a mere 1.3 seconds. This speed reaches 300,000 kilometers every single second, the ultimate speed limit of the universe. For comparison, the fastest human-made object, the Parker Solar Probe, only reaches a fraction of that velocity. Even at 600,000 kilometers per hour, the probe is standing still compared to light. This brings us to a crucial physics problem involving Einstein's famous theory of relativity. As an object approaches the speed of light, its mass actually begins to increase toward infinity. Even more mind-boggling is the fact that time itself slows down for the moving object. Because mass increases, you would need an infinite amount of energy to push that needle to 100% light speed. But what if an advanced alien civilization engineered a way to reach 99.9% of that speed? The needle is now a kinetic bomb carrying an unimaginable amount of energy despite its small size. It acts much like a bullet, where extreme speed compensates for a lack of physical mass. We are about to witness the moment this needle finally makes contact with the Earth's surface. Imagine the needle targeting the most iconic location in New York's Central Park. As it hurtles through the atmosphere, it generates an enormous amount of friction and heat. We often see spacecraft ignite during re-entry, but the needle's speed is orders of magnitude higher. There is a chance the needle could disintegrate before impact, but for this scenario, let's assume it survives. This fiery projectile hits the park, triggering an explosion that defies standard measurement. The energy released would be over 100 times more powerful than a modern nuclear bomb. Trees, grass, and people in the park would be instantly incinerated by the radiating heat. Surrounding buildings would collapse like falling Jenga towers under the force of the shockwave. A giant fireball would expand outward, followed by a shockwave that rocks the entire region. The destruction would not stop at the city limits, shaking nearby states like New Jersey to their core. Seismologists would record an earthquake equivalent to a 7.3 on the Richter scale. History shows us that a 7.9 earthquake in San Francisco once destroyed 28,000 buildings. The needle's impact could potentially cause similar devastation, localized but incredibly intense. If you lived on the other side of the globe, you might be lucky enough to survive the initial blast. However, the fallout and environmental changes could eventually reach every corner of the Earth. Now, let's pivot and consider what happens when this cosmic needle strikes the ocean instead of land. The impact would cause a massive column of water to erupt miles into the atmosphere. Scientists estimate that while the splash would be giant, it wouldn't necessarily cause a global tsunami. Tsunamis require massive geological shifts over vast areas, whereas the needle is just a single point of impact. Even Mother Nature's natural disasters like the 2004 Indian Ocean tsunami are far more powerful than this needle. But the most terrifying scenario involves the needle hitting an active volcano and triggering a chain reaction. To understand the catastrophe, we must first address why a simple needle cannot actually reach the speed of light. Light speed represents the absolute speed limit of our known universe. According to Albert Einstein's theory of special relativity, things get very strange as you approach this limit. As an object's speed increases toward that of light, its mass also begins to increase. The faster the needle moves, the heavier it effectively becomes to the universe. To push this increasing mass even faster requires more and more energy. To reach 100% of the speed of light, you would need an infinite amount of energy. Since the universe doesn't have infinite energy to give, a true light-speed needle is impossible. But what if an advanced alien civilization found a way to cheat the system? Instead of hitting the impossible 100%, they engineer a needle to reach 99.9% light speed. At 99.9%, the energy requirements are still astronomical, but mathematically finite. The needle is now more of a kinetic bomb than a piece of metal. Because of its incredible velocity, time itself begins to behave differently for the needle. For the needle, a journey across the solar system would feel like a mere heartbeat. This tiny sliver of steel is now packing the kinetic punch of 1,000 nuclear warheads. Its mass has ballooned to many times its original resting weight. Every atom within the needle is under extreme relativistic stress. The alien engineers finalized the trajectory, aiming directly at the blue marble in the distance. A massive magnetic pulse is unleashed from the megastructure. The needle is caught in the wave and propelled forward with terrifying force. It crosses the distance between the Moon and Earth in just over a second. There is no time for radar to detect it and no time for humans to react. The needle is now a messenger of doom, carrying energy that defies comprehension. At this speed, the atmosphere doesn't behave like gas, it behaves like a solid wall. Friction begins to tear at the needle's surface, even at the atomic level. The metal starts to liquefy, yet it maintains its shape due to the extreme forward momentum. It is now traveling through the air faster than the molecules can move out of its way. This compression creates temperatures hotter than the surface of the sun. Below, the city of New York sits oblivious to the cosmic bullet aimed at its heart. The needle's path is locked onto the lush greenery of Central Park. The shockwave trailing the needle begins to shatter windows miles above the ground. The kinetic energy formula, half mass times velocity squared, is reaching terrifying totals. We are looking at a total energy release of over 100 megatons from a single gram of steel. As it drops below 10,000 feet, the air itself begins to ignite in its wake. The sonic boom is so powerful it levels trees before the needle even arrives. The needle is now a blinding white point of light, brighter than 1,000 suns. Time seems to stretch as the tip of the needle finally touches a single blade of grass. In that microsecond, the laws of biology and chemistry cease to matter. The ground begins to buckle as the kinetic energy is transferred into the Earth's crust. Just as the first spark of the explosion blooms, a mysterious signal interrupts the aliens' feed. Something else was waiting in the atmosphere, and the true destruction is only beginning. The needle streaks across the sky like a fallen star, leaving a trail of ionized air in its wake. Friction begins to scream against the object's surface, though its incredible velocity defies all laws of aerodynamics. Below, the lush green expanse of Central Park remains momentarily peaceful, unaware of the doom approaching at 300,000 kilometers per second. The needle makes contact with the soil of the park, and the laws of physics transform mass into pure, unadulterated energy. In a microsecond, the kinetic energy of the needle is released, equaling the power of over 100 nuclear bombs. Every blade of grass, every ancient oak tree, and every living thing in the park is instantly incinerated. The heat is so intense that the very air molecules ignite, turning the atmosphere into a pressurized kiln. Skyscrapers surrounding the park, like the iconic Billionaire's Row, are hit by a wall of pressure that no engineering can withstand. Massive steel and concrete structures begin to collapse, like falling Jenga towers under the force of the shockwave. A giant fireball rises where the sheet metal once was, swelling to a size that dwarfs the highest peaks of the city. This is not a conventional explosion, but a hypervelocity impact that liquefies the bedrock of Manhattan. The shockwave pulses outward in visible ripples, moving faster than the speed of sound through the city streets. Thousands of fires ignite simultaneously across the 5 boroughs as the radiant heat sets everything flammable ablaze. New York City is no longer a metropolis. It has become a literal crater in the making. The blast wave reaches the Hudson River, vaporizing the water surface instantly into a wall of steam. Across the water in New Jersey, the ground begins to heave and buckle as the seismic energy arrives. Seismographs across the continent spike as the impact registers as a massive 7.3 magnitude earthquake. This energy release is comparable to the 1906 San Francisco earthquake, but concentrated in a single, violent moment. The sound of the impact arrives seconds later, a thunderclap so loud it deafens anyone within a 50-mile radius. Dust and pulverized concrete are thrown miles into the stratosphere, blotting out the sun for the entire tri-state area. Emergency sirens are cut short as power grids across the Northeast fail under the electromagnetic pulse of the impact. The needle itself has long since vaporized, but the hole it punched into the earth remains a searing wound. The silence that follows the initial blast is punctuated only by the roar of uncontrollable fires. Bridges connecting the island to the mainland have snapped like toothpicks, leaving Manhattan isolated in its destruction. Calculations show that the kinetic energy of a single gram of matter at this speed is enough to flatten a city. The atmosphere around the impact site has been stripped of oxygen, replaced by superheated nitrogen and carbon. From space, the Earth looks as though it has been hit by a cosmic bullet, a glowing red dot appearing on the blue marble. The debris cloud begins to spread, carried by high-altitude winds toward the Atlantic Ocean. Below the surface, the subway tunnels have collapsed, crushed by the immense weight of the shifting tectonic plate. This is the reality of cosmic kinetic energy, a tiny object with the power of a world ender. But the destruction isn't limited to the physical blast. The pressure wave continues to travel through the crust. As the dust settles, the crater reveals a terrifying truth about the needle's penetration depth. The local devastation is absolute, and the regional effects are just starting to be felt. The sheer speed of the needle meant that the air couldn't even move aside, resulting in nuclear fusion at the tip. We are seeing the death of a city in a matter of seconds, all because of an object no larger than a sewing tool. Survival within the blast radius was impossible, and the thermal radiation has reached far into the suburbs. The secondary effects, including firestorms and toxic rain, are now beginning to form in the destabilized atmosphere. While New York bears the brunt, the energy continues to dissipate through the Earth's mantle. But what if the point of impact wasn't a city park, but something far more volatile, hidden deep beneath the surface? The shockwaves are triggering dormant fault lines, and a far greater geological nightmare is about to wake up. The initial explosion in Central Park is only the beginning of the planetary trauma. Underneath the scorched Earth, the kinetic energy of the needle converts into raw seismic power. Scientific estimates suggest the release of energy would equate to a magnitude 7.3 earthquake. To understand this scale, we must look back at the 1906 disaster that leveled San Francisco. That historic event destroyed 28,000 buildings and claimed hundreds of lives. Now, imagine that same level of tectonic violence concentrated directly under New York City. The ground shifts violently, turning the foundations of skyscrapers into liquid sand. The shock waves do not stop at the city limits, racing outward into the neighboring state of New Jersey. Unlike a typical earthquake, this seismic event is caused by a point source kinetic impact. This means the energy is most intense at the strike zone, but its reach is still terrifyingly broad. Buildings designed for wind resistance are utterly helpless against the vertical acceleration of the strike. In the first few seconds, the seismic waves travel at miles per second through the lithosphere. Bridges connecting the boroughs begin to sway and snap like violin strings. Below the streets, the subway tunnels collapse as the earth around them compresses. For those far away, the horizon itself seems to jump as the shockwave arrives. This impact triggers a phenomenon known as secondary shaking across the entire region. The energy is so dense that it could potentially disturb dormant fault lines hidden for centuries. Geologists would be stunned to see a single needle do the work of a tectonic plate shift. The sheer speed of the needle means the Earth doesn't have time to react elastically, it simply shatters. Within minutes, the once solid ground has become a landscape of jagged peaks and deep fissures. However, the damage might be localized compared to a global catastrophe depending on the strike point. If you lived in London or Tokyo, you might only feel a slight vibration, unaware of the horror. But for the East Coast, the infrastructure would be effectively reset to the Stone Age. The seismic energy eventually dissipates, but not before altering the topography of the region forever. Dust from the geological upheaval rises to meet the smoke from the fires, choking the atmosphere. Scientists would find that the needle itself has likely been vaporized into a cloud of metallic ions. But the ghost of its momentum lives on in the shifting tectonic plates. The seismic signature of this event would be unlike anything ever recorded by humanity. In many ways, the shock waves are more dangerous than the initial flash, for they travel through the very ground we stand on. Water mains burst and gas lines rupture, turning the trembling city into a landscape of geysers and flames. This is the reality of kinetic energy. It cannot be destroyed, only transformed. Every skyscraper that falls adds to the seismic chaos, creating its own local tremor upon impact. The needle's passage has created a vacuum that now collapses with the force of a thunderclap. This atmospheric punch hammers the ground a second time, compounding the geological damage. We often think of space as empty, but the needle proves that even a speck can move the world. The local devastation is absolute, but a larger question remains about the planetary equilibrium. The Earth's rotation might even be minutely affected by such a concentrated blow. As the dust settles over the ruined city, the geological ripples continue to travel through the oceans. We have seen what happens when the target is solid rock and concrete. But what if the needle doesn't find the land and instead plunges into the deepest parts of our world's oceans? If the needle misses the continents, it finds a far deeper grave in the blue heart of our planet, The moment of impact is not a splash, but a violent transformation of matter into energy. At these speeds, the water behaves less like a liquid and more like a solid wall. A massive column of superheated steam and vaporized seawater erupts kilometers into the atmosphere. This event mirrors the 1946 Baker test, where a nuclear device was detonated beneath the waves. That historic blast created a plume 2 kilometers high, yet it was only a fraction of the needle's potential power. You might expect a globe-spanning tsunami to wipe out every coastline on Earth. However, the physics of a needle impact are fundamentally different from an earthquake. Tsunamis require the displacement of massive amounts of water over a vast area along the seabed. Our needle is a single-point event, focusing its energy in a localized, albeit massive, explosion. While coastal regions would face significant waves, they would not face the 2004 Indian Ocean disaster's scale. Mother Nature's geological shifts remain far more powerful than this tiny light-speed intruder. The needle continues its journey, passing through the water and into the crust with terrifying ease. Pressure at these depths is immense, but it is nothing compared to the kinetic force of the projectile. As it burrows into the Earth, it creates a hole that shouldn't exist. This puncture isn't just a wound, it's a straw that allows the planet's internal pressure to scream outward. Liquid physics explains why the water doesn't just fill the void instantly. The sheer heat of the impact turns the surrounding water into a plasma shield. For a moment, a pocket of vacuum-like conditions exists where the needle passed. The shock waves move faster through the water than they do through the air, vibrating the very foundations of the sea. This acoustic energy would be lethal to any marine life within hundreds of kilometers. Whales and dolphins would feel the impact through their sonar long before the physical wave reached them. The thermal energy release would boil cubic kilometers of ocean in seconds. The resulting salt mist and steam would alter the local weather patterns for weeks. Unlike the land impact, the ocean acts as a massive heat sink, absorbing much of the initial radiation. This might seem like a safer scenario, but it only hides the danger beneath the surface. The needle hasn't stopped. It's simply changing the theater of destruction. Every meter it travels deeper increases the chance of hitting a tectonic nerve. Even a small needle can act as a trigger for much larger, pre-existing geological stresses. While we escaped a tsunami, we may have inadvertently invited a much hotter guest to the party. The water above begins to settle, but the silence is deceptive. The kinetic energy has been transferred, but energy cannot be destroyed, only changed in form. Much of that energy is now heat, trapped under the weight of billions of tons of water. This heat begins to expand, looking for an exit through the Earth's crust. What happens when that needle-thin hole becomes a highway for the Earth's molten core? The ocean impact gave us a reprieve from immediate fire, but it may have doomed us to a slower burn. Our world is a complex machine, and this needle has just jammed the gears. We have analyzed the land and the sea, but what of the individual life caught in the crossfire? The needle's path is absolute, indifferent to whatever or whoever stands in its way. But what if the next target isn't a city or an ocean, but a single human being? And what if that impact triggers the final fiery breath of our world? The mathematical abstraction of a needle strike becomes horrifyingly personal when we consider its impact on a single human target. At 99.9% the speed of light, the needle does not merely pierce the body, it delivers an infinite well of kinetic energy. For the person standing in its path, there is no time for fear or the sensation of pain. You would be the first and last thing to absorb a force greater than 1,000 nuclear suns. Death occurs instantly at a speed faster than the human nervous system can transmit a signal to the brain. While the individual is vaporized, the energy does not stop. It drives deep into the crust beneath their feet. But the scenario turns from a personal tragedy to a global apocalypse if that needle strikes a volcanic site. The needle acts as a cosmic key, unlocking the immense, pent-up pressure of the Earth's magma chambers. Within seconds, the needle disrupts the delicate balance of the subterranean reservoir. A series of massive volcanic eruptions would trigger across the region, unlike anything seen in human history. We have seen this before, such as the Toba eruption that nearly wiped out the human race 74,000 years ago. In that era, only a few thousand resilient survivors managed to endure the following centuries. Today, the scale of the disaster would be magnified by our global interdependence and massive population. As the needle's impact forced open the Earth, billions of tons of ash would be hurled into the stratosphere. This debris would act as a planetary shroud, beginning to block the very light that sustains life. The immediate thermal blast is only the beginning of a much longer, colder nightmare. Within weeks, the global temperature would begin a precipitous and unstoppable decline. Crops in the world's breadbaskets would fail as the growing seasons vanished overnight. The ecological chain, carefully balanced over millions of years, would start to snap link by link. Herbivores would be the first to succumb to starvation, followed quickly by the predators that hunt them. Humanity would find itself in a desperate race against a clock that doesn't care about our technology. This is the onset of a nuclear winter caused by a sewing tool traveling at the speed of a god. For 10 years or longer, the sun would remain a memory, hidden behind the sulfurous veil. Global starvation would likely claim the majority of the 8 billion people currently inhabiting the planet. Only isolated pockets in the southern hemisphere, like parts of Australia, might see enough light to grow food. But these regions could never sustain the weight of a fleeing global population. We would be forced back into a primitive struggle for existence that we haven't faced in millennia. The needle is a reminder that the universe doesn't need a giant asteroid to break us, just a tiny object with enough speed. Every structure, every achievement, and every life could be erased in a single, silent millisecond. The physics of light speed turns the mundane into the mythical and the needle into a thunderbolt. We live on a fragile sphere, protected only by the vast distances of space and the laws of physics we are only beginning to understand. If an advanced civilization ever decided to launch such a projectile, we would never even see it coming. The first sign of the end would be the very impact that vaporizes the atmosphere. Total extinction is a high-speed game of chance where we have already won billions of times by simply existing. The needle impact on a human target was a small-scale horror, but its geological aftermath is a planetary funeral. We are left to wonder if any remnant of our culture would survive the decade of darkness. The pressure is building, both in the magma chambers below and in the silent reaches of space. Nature has a way of balancing the scales, often with a violence that defies our comprehension. As the ash settles and the world turns cold, we must look to the heavens for the next potential threat. But while we fear the light-speed needle, perhaps the most bizarre and unexpected danger is currently orbiting right above our heads. The immediate fireballs have faded, but a much more persistent terror is now ascending into the stratosphere. billions of tons of fine silicate ash and sulfur aerosols begin to spread across the globe like a dark, suffocating blanket. Within weeks, the sun becomes nothing more than a pale, ghostly disk in a perpetually leaden sky. This is the onset of a nuclear winter, a period where the sun's rays are blocked from reaching the surface. Global temperatures begin a rapid and relentless plunge, turning summer landscapes into frozen wastes. Without sunlight, the fundamental process of photosynthesis grinds to a halt across the planet. Vast agricultural belts that once fed billions are transformed into barren, dust-choked graveyards. The collapse of the plant kingdom triggers a domino effect through every level of the ecological chain. Herbivorous animals die off first, leaving carnivores to fight over the dwindling remains of the old world. For humanity, the challenge of surviving 10 years without a single harvest is almost insurmountable. History offers a grim precedent. The Toba eruption nearly 74,000 years ago reduced our species to a few thousand survivors. Today, our global population of 8 billion people relies on a delicate, just-in-time food supply that would vanish in weeks. Scientists suggest that a few isolated pockets in the southern hemisphere, like Australia and New Zealand, might remain viable. These regions could potentially produce food under low light and low temperature conditions, serving as humanity's final lifeboats. However, these refugee lands could only support a tiny fraction of our current population. The vast majority of the human race would succumb to the cold, famine, and the resulting societal collapse. Those who remain would emerge into a world fundamentally altered, a hardier and perhaps more cautious remnant of a lost civilization. This cooling of the Earth isn't just a local event, it affects the very chemistry of the oceans as well. The absorption of sulfur into the water leads to acidification, killing off coral reefs and the base of the marine food web. As the ash lingers, the very air becomes toxic to breathe without filtration in many parts of the northern hemisphere. Communication networks fail as satellite signals struggle to penetrate the ionospheric interference caused by the impact's EMP. Humanity is plunged back into a pre-industrial isolation, with each community left to fend for itself in the dark. We often think of space as a vacuum of nothingness, but even the smallest stowaway can change our fate. The energy of that single needle was enough to rewrite the history of biology on our planet. But let's step back from the brink of total annihilation for a moment. Not every object falling from space arrives at 99.9% of the speed of light. Most things that fall toward us follow the much slower, more predictable laws of orbital mechanics. Sometimes, these objects are so mundane that their journey through the fire of re-entry becomes a cosmic joke. Consider the International Space Station, a marvel of engineering orbiting 400 kilometers above the surface. Up there, astronauts live in a world where dropping a tool means losing it to the void forever. But what if you dropped something much more organic? Something you'd never expect to find in a vacuum? Atmospheric friction is a powerful force, capable of generating enough heat to melt heat shields. If it can melt metal, surely it can cook a piece of meat to perfection, right? The physics of re-entry cooking are surprisingly complex and involve a battle between extreme heat and freezing altitudes. Unlike our light-speed needle, a falling steak doesn't have the mass to maintain its velocity for long. It faces a gauntlet of sub-zero temperatures before it ever hits the lower, thicker air. The result of this orbital barbecue is less of a gourmet meal and more of a scientific disaster. But there is a much bigger problem than just a bad dinner. In space, what goes around literally comes around, and it does so with lethal momentum. That stake you just dropped isn't falling to Earth. It's becoming a high-velocity projectile aimed directly at your only home in the stars. Having survived the needle's light-speed apocalypse, we now turn to a much more relatable, yet equally impossible cosmic experiment. Imagine an astronaut stepping out of the airlock, not with a tool, but with a perfectly marbled ribeye. To simply drop the stake, you must first understand that dropping doesn't exist in the vacuum of low Earth orbit. The stake is currently traveling at 17,500 miles per hour, locked in a perpetual fall. If you just let go, the stake would simply float alongside the space station like a loyal, meaty companion. To get it to fall to Earth, you have to throw it backward with enough force to cancel out its orbital velocity. As the stake loses speed, gravity finally begins to win the tug-of-war against centrifugal force. It enters the upper reaches of the atmosphere where the air is thin but the speed is still astronomical. At Mach 25, the air in front of the stake can't move out of the way fast enough. This creates a bow shock of compressed gas that reaches temperatures hotter than the surface of the sun. You might think this is the perfect way to get a quick sear on your dinner. Unfortunately, the laws of thermodynamics are not kind to orbital chefs. The heat is so intense and the time is so short that the inside of the steak remains frozen solid. As it descends further, the increasing air pressure begins to tear the charred meat apart. Your expensive ribeye has now become a very short-lived meteor. If by some miracle a fragment survived, it would reach terminal velocity and cool down rapidly. By the time it hit the ground, it would be a cold, soggy piece of charcoal covered in atmospheric pollutants. This highlights the fundamental difference between the needle and the stake. Mass and velocity dictate destiny. The needle possessed enough energy to rearrange the crust of our planet. The stake, meanwhile, is a victim of the very atmosphere that protected us from the needle's smaller debris. These thought experiments serve a greater purpose than mere curiosity. They help us understand the kinetic energy that governs the movement of every asteroid and comet in our solar system. We learn that at high enough speeds, matter stops behaving like solids and starts behaving like energy. Whether it is a needle at the speed of light or a stake from the ISS, the universe plays by a strict set of rules. By mastering these rules, we can begin to prepare for the real impacts that may one day head our way. We have seen the darkness of a nuclear winter and the heat of a light-speed collision. But through the lens of science, we have also seen the resilience of our world. The Earth has survived billions of years of bombardment, and it will survive many more. And if you ever find yourself on the ISS with a craving for BBQ, just remember to use the microwave. The stake experiment reminds us that space is a place of wonder, even in its most ridiculous forms. Our journey through the physics of the extreme has come to its natural conclusion. We have explored the limits of speed, energy, and even culinary patience. The chaos of the light-speed needle is now just a data point in our collective knowledge. The conflicts of nature are resolved by the very laws that created them. Every impact, no matter how small or how devastating, leaves a mark that tells a story. We are the observers of this cosmic theater, and our curiosity is the greatest shield we possess. Rest easy knowing that while the universe is a violent place, it is also a predictable one. Our world remains safe. The needle remains a theory, and the stake remains on our plates. The simulation is over, but the wonders of physics continue forever. Thank you for joining us on this journey through the impossible and the delicious.